Hi everyone. This is the fourth week for the course Fluid Dynamics for Astrophysics, and this is the live session. I'm Suprita Bhomik, and I'll be conducting this live session. So, let's start with the revision of the material covered in this week's lecture. Okay, so this week we learned about dimensionless quantities, how to simplify equations of fluids. Uh, what we essentially do is look at the terms and compare the different terms and their contributions. And if we and that allows us to, let's say, by computing the ratios of contributions of two terms, if the ratio turns out to be smaller or larger, much smaller, much larger than one, we're allowed to drop a few terms from the equation, and that allows us to uh, solve for a simpler equation by dropping a few terms. Uh, and that and in this week's lecture, we looked at a few dimensionless quantities. Um so one of the examples was the Mach number, which was essentially the ratio of the inertial term versus the pressure gradient term in the Navier-Stokes equation. So let's say you have the Navier-Stokes equation, right? So the left-hand side, if you remember, there were two terms which was merged to give you this total Lagrangian derivative ddt. On the left-hand side, you had something like del V del T plus rho V dot grad V. This and this was merged to give you this. Uh, and there was also a body force term that we dropped, we neglected for now. All right. So what we will do is we will compare the inertial term, which is the term on the left-hand side, which is the response of the fluid, or rather the term which is giving you the flow profile as a response to pressure, body forces, viscosity of the fluid, and so on, right? So the Mach number is the ratio of the inertial term and the pressure gradient term. And this turns out to be V squared by Ca squared. How does that happen? Well, dV dt was basically, or dV dt is basically the change in V, dV change in the velocity in a time dt, right? So we can write this dV dt as some characteristic velocity divided by some characteristic time. And this time can be written, or rather, the cu is basically some characteristic length scale divided by some time scale t. So I can substitute for t in terms of u and l and write this as u square by l, right? And this gradient of p is nothing but the spatial derivative of the pressure, which I can rewrite as del P del rho sum rho by L. Del P del rho is the speed of sound squared. So this is the speed of sound squared rho by L. So overall, this ratio turns out to be u squared by L divided by Ca squared rho by L. And of course, there's a rho over here. So I write this rho. Rho cancels out. And so does L, leaving you with some u squared by Ca squared. And u and v over here are used interchangeably. They mean the same thing. They refer to some characteristic velocity of the system. Okay, if that is fine. Uh, all right. And we'll look at the significance of Mach number later on. Okay. The second example of dimensionless quantity was Reynolds number, which was, once again, we compared two terms, and our aim is to see whether this quantity, this ratio is smaller or greater than 1. If it is smaller than 1, we can, let's say, ignore if it's smaller than 1, we can ignore the numerator as compared to the denominator, and so on. So the Reynolds number is the inertial term divided by the viscous drag. This is a comparison between the contribution of the inertial term versus the viscous drag. And if you repeat the same procedure that we did for Mach number, you will see that it is actually VL by nu, where nu arises because we redefined mu, which was a coefficient of viscosity, as rho times nu. This nu is this nu over here. So if you recompute, if you use the exact same logic we used for Mach number and use some characteristic length scales and substitute for dV dt and this Laplacian V, you will see you will end up with this. Have you tried doing this, or do you want me to do this here? Or is this clear how one will get this quantity as a result of taking this ratio?
I think this is fine.
Okay, good. Okay. So, out of all of this, what is the significance? Because Reynolds number was something that was discussed at length in these lectures. So, uh, what is the significance of Reynolds number? For that, we will discuss when do we expect a flow to be laminar? When do we expect the flow? And by laminar, what we really mean is non-turbulent, non-chaotic, some nice flow, right? So when do we expect the flows to be laminar? First of all, whenever I say a laminar flow, one would really imagine steady states, right? Where the velocity of the fluid profile does not change as a function of time, right? What that means is, at any given point of time, the fluid parcel remains unaccelerated. And if a fluid parcel, if the fluid elements have to remain unaccelerated, then the forces acting on this parcel have to balance each other. Now, if you look at the Navier-Stokes equation, you will see that the forces at play are the pressure gradient term and the viscous term. The pressure gradient term is what causes the flow. It is what we say or claim is causing the fluid to flow from one point to another point. And the viscosity term is the restoring force, or is the drag to the fluid parcels. Now, in situations where the viscous force is comparable to the inertial term, that is when we can expect to have a steady state, because that is exactly when this term can go to zero. If the viscous term is much smaller than the pressure gradient term, you can't hope to achieve a steady state. The fluid elements will be accelerated, and that will introduce turbulence in the system, that will introduce chaos in the system, right? So when you have high viscosity, and what does high viscosity means in terms of Reynolds number? Remember, Reynolds number was the ratio of inertial term to the viscous drag. When you have high viscosity, which means when you have no low Reynolds number, that is when you can expect steady states. Okay, and that is also something where you can think about a time in your life where you have ever seen a turbulent flow of honey. Honey is a very viscous fluid. It is very difficult to and very unnatural to have turbulent flow in something as viscous as honey, right? So you would, if you want steady states, you would actually want large viscosity. Okay. Second thing is low velocities and small characteristic length scales. So if you have really large velocities of your fluid, once again you can expect the flow to become non-laminar. You can expect turbulence in your system. That is something what you must have also observed in everyday lives. Same thing with small characteristic length scales, but once again, not too small. Now, can you explain, or do you have a reason why we can't consider too small of length scales if we want laminar flows?
By the way, means how are you defining this characteristic length scale in this problem?
Characteristic length scales, of course, this definition would differ from system to system, but think of it as this. If you're considering fluid flowing through a pipe, right? The length over which this fluid is flowing, let's say that is your characteristic length scale.
Or like if I have a river flowing, then what will be the characteristic length scale in that case?
A river flowing is okay. So a river flowing would have, let's say, lots of banks, right? right?
Yes, yes.
Now, it's impossible to compute the flow profile of the fluid throughout uh, throughout the banks. So what one would do is, let's say, compute segments.
Okay.
So and of course, it's impossible to or impractical to hope to explain the flow profile of the fluid throughout the river. You can't give such descriptions of the system.
Okay.
So you would divide the, let's say, the river into small length scales, and then this would be, let's say, your macroscopic or characteristic length scale.
Okay, like
Okay.
in this, in a Poisson flow, we have this pi p r to the 4 divided by 8 mu L. In that
Hmm.
case, that L is that characteristic length, right?
What is it?
The Poisson flow.
What is L in there?
No, no, that flow through a pipe, the length of the pipe.
Yeah. Absolutely, absolutely. Yeah, correct. Right. So why can't we take very small length scales, or let's say I'm considering this flow through a pipe, right? Now I want to say whenever I want to claim whether my flow is laminar or not, I have to claim whether my flow is laminar or not over a certain length scale, right? So I can claim that my flow is laminar throughout the flow. My fluid flows in a laminar way throughout this pipe, that the length of this pipe is L. But why can't I do it if I, let's say, not make the statement for this length scale, but for a very, very small length scale?
Because that will break the continuum hypothesis.
Absolutely. Very nice, very nice. That will break my continuum hypothesis. So I have to be careful to not go to very, very small length scales, right? And once again, I can't go to really large length scales because I don't know what will happen to my system, right? In general, if you have a high Reynolds number, you can expect a turbulent flow. Because remember, Reynolds number was sum UL divided by mu. So if this L is large or your velocity is large, you can expect turbulent flows. U is large, L is large, as opposed to what? As opposed to nu. So when your viscous force, when your viscous term starts to lag behind or can't keep up with the inertial term, that is when you have unsteady states, right? And that's when you can forget about the laminar description. That's when you have a turbulent uh, flow. Okay, yeah. So just to repeat myself, when can you expect the flow to be turbulent? You have turbulent flows when you have the inertial forces dominating over the drag forces, over the viscous forces, right? So in those scenarios, you will have things like chaotic flows, vortex shedding. Vortex shedding was something that was discussed in the lectures. If you remember that, let's say you have a flow profile which is directed towards the right, and you have a solid object here, right? What you would happen is you will see vortices behind the solid object, behind in the direction, in the sense that the forward will be the direction from where the fluid is coming from. Okay, good. Few more examples. The example of plasma beta, which was the ratio of gas pressure versus magnetic pressure, right? Now, why would magnetic lines exert pressure? This is something you would read because, of course, this is a course of fluid dynamics in astrophysics. You would have to inevitably read about plasma physics at some point. The lecturer will introduce you to some basic plasma physics, and then you will see that if you have plasma material, plasma is nothing but just a bunch of charged particles, right? This could be electrons, ions, something. Now, if you have magnetic field lines passing through plasma, then the physics of plasma physics will tell you that these B field lines have a tendency to remain frozen in the plasma. And now if you apply the fluid description, the continuum description onto the plasma, you will see that, of course, this plasma, this fluid, can have a certain velocity v. These magnetic field lines are frozen in the plasma in such a way that they will try to move with this fluid parcel, right? And these B field lines, it's best to think about them as rubber bands. So when they are stretched or squeezed, they will have some resistance to squeezing or stretching, they will try to retain whatever beefy lines they are. Okay, that's where the magnetic pressure comes in. Next is something called the magnetic Reynolds number. Now, this was a measure of the ability of the material, or this was a measure of of how strongly the beefy lines are coupled to the fluid, right? So you would have seen this was inversely proportional to sum 1 by eta, where eta was the diffusion coefficient, and this is exactly this. Eta is this term that arises with libration of P. Now, this is something called the magnetic diffusion equation. This is of course not yet introduced to you. I've just put it here to uh, relate this to the idea of dissipation or loss of B field lines in the fluid, right? So, if you look at this equation, it will tell you that let's say you're considering plasma and B field lines, magnetic field lines in the plasma, the rate at which magnetic field is dissipated, or the rate of change of B field lines depends on two terms. This is your usual induction term. This is the term that tells you about the loss of magnetic field lines. And magnetic Reynolds number is basically a ratio of these two terms. Okay.
What is that sigma there?
Sigma is the electrical, what do you call it? Conductivity. Yeah.
Okay, conductivity.
Yeah.
Okay.
Okay. Next comes the concept of dynamic similarity. Uh, now, starting with this idea, one has to think of viscosity as small perturbations to an unperturbed system. So let's say your original system that you were working with just had an inertial term. Forget about body forces for now. It just had an inertial term. Now what you do is you introduce small perturbations in the guise of viscosity to your system. That is what one does in perturbation system, right? You have your unperturbed system and then you want to solve your actual system which does have the small perturbations, and you treat these viscosity as very small disturbances to your system. Okay, so what you really want to do is, if you want to solve this Navier-Stokes equation, whose solutions are given by this U will be given by some solution U, where U is the velocity of your unperturbed system, plus some perturbation. This is what one would do in, let's say, if you have done perturbation theory in quantum mechanics, this is exactly what one does. Okay, all right. So this is what you're supposed to think of the solution of this Navier-Stokes equation as the perturbation to some system where you did not have any viscosity. Okay. Now, what we would like to do is realize that if you take this equation, if you take this system and solve it at some length scale L, let's say you're solving this. So this was an example that was repeatedly given in the lectures. Let's say you're solving for the flow profile of seawater around a ship, a huge ship. And let's say you compare it with a toy model in a bathtub. You will see that this equation is not invariant under scaling of lengths and velocities. Okay, because this has dimensionful quantities. U is a dimensionful quantity, dimensions being L by T, and so on. So if you scale x to, let's say, some lambda x, this is not going to give you the same profile. I mean, it's not very clear whether it will do so. As long as you're working with dimensionful quantities, it's not very clear what is going on. Okay. So what we want to do now is make all of the terms arising in this equation dimensionless. How will we do that? We will reparameterize the length scales x, divide them by L, and call it the new x prime. Do the same with hue and with pressure, and substitute this over here. Now, did you try to derive this equation in terms of this? This was given as an exercise in the lectures. Okay, in case it is not very clear how it can be done, let me do it once. So what we are doing is we have redefined x, u, and p to x prime, u prime, and p prime. And now we want to rederive this equation in terms of x prime, u prime, and p prime. Okay. So now we start with, let's say, the first term over here. So rho over here remains as it is. U I have redefined to be this u vector divided by u, where u is, this capital U is a characteristic velocity. And this ratio, what this does is it makes u prime dimensionless. That is what I wanted to do. I wanted to rewrite this equation in terms of dimensionless quantities. And this gives me a rho u times u prime, where I've written this u as capital U times u prime. And then comes a gradient. This is a spatial derivative. Now, all of the spatial derivatives have the form of del x. But x I have redefined as L times x prime. So this becomes 1 by L del x prime. But what is del x prime? It is grad in the primed variables, right? So what I can do is I can rewrite this as 1 by L. I've just rewritten this grad in the primed grad. And once again, I have a u over here and I will substitute this with capital U times u prime, which gives me what? It gives me u square by L. U from here, a u from here, and L from here. This gives me rho u square by L, which is basically this. Okay? Okay. Next comes a gradient of P. And as I discussed, all my gradients will become 1 by L grad prime. Is this clear why? Is this clear why? Okay, I hope that was a yes. Uh, so what happens is I will rewrite this as minus 1 by L grad prime. And then I have redefined P to be rho u squared times P prime. So I'm substituting for P, and P has been redefined to rho u squared times P prime. So this should actually be P prime. So what this gives me is a rho u squared by L with a minus sign over here. Is this clear?
Yes.
Okay, thanks. Next thing is mu. Now mu is the coefficient of viscosity, and it's the coefficient of viscosity at all length scales. We're not going to scale mu, but we do have to scale this Laplacian of u. U is scaled to, once again, U is scaled to capital U prime, and Laplacian will be scaled to L square this, which gives me this term. Okay, if that's fine,
Why
introducing
aren't
these
we
two.
scaling mu? Because even though mu has some dimensions.
Mu does have dimensions, but think about the physics of it. The coefficient of viscosity for a fluid uh, depends on the transport phenomena. So it can be explained from the microscopics, right? From the microscopic description. Now, the microscopic description can be related to the macroscopic picture for all length scales of the macroscopic picture,
Okay.
right? So the microscopic description would hold, let's say, at the particle level, whatever be the particle size of So that the microscopic description is the correct description uh, at length scales which are comparable to the, let's say, interparticle distances or particle size, right? But when you go to large length scales, once you have related the microscopic picture to the macroscopic picture, once you know how to get viscosity from the particle description, then the coefficient of viscosity is just the same.
Okay.
Okay. So we don't scale mu. It is indeed true, but think about the physics of it. Okay. All right. So once we make these changes and we make these changes in this equation, it gives us this equation. Okay. We just bring this term to the right, cancel it with this term, and in the second term, it will give me this factor. All right. Uh, but this factor is exactly inverse of the Reynolds number. If you remember, the Reynolds number was UL by mu, where sorry, uh, nu. Reynolds number is dimensionless. Sorry, mu has some dimension. Reynolds number is UL by nu, and this nu was mu by rho, which is exactly the inverse of this term. So I write this as 1 by Reynolds number. Now, this equation has all the dimensionless quantities, right? And this is a nice equation to work with because you know that as long as you are working with two systems which differ in sizes. Now, let's say by two systems, I mean two fluid systems with some solid objects submerged in them, right? Now, these solid objects, as long as they have the same geometric shape, if they are scaled versions of each other, if these systems are scaled versions of each other, this equation tells you that the flow profile for both of the systems will be the same. Okay. Okay. I'm going to solve one more exercise, a couple more exercises that were left in the lectures. Uh, One of them was deriving the vorticity equation for viscous barotropic flows. And you had to show that this is the equation it follows. So if you remember, the vorticity equation for inviscid barotropic flows was derived in the lectures, and that equation only had this term. Barotropicity removed a term which had terms like, see, remember barotropic, we call fluids barotropic if their pressure can be expressed as some function of their densities. But this was not done for viscous fluids, and this was asked to, and we were asked to show that this is the equation it follows. So what do we start with? We of course start with the Navier-Stokes equation. Earlier we started with the Euler equation because we were deriving the vorticity equation for inviscid flows. Now we have to keep viscosity in mind, so we start with the Navier-Stokes equation. This is the inertial term. This is the pressure gradient term. This is the viscosity, the viscous force. Okay. Uh,
In all this exercise, we are neglecting body forces.
yes, yes,
Okay.
yes. Uh, it is, I think, trivial to reintroduce body forces. If at any point of time if you want to worry about body forces and you see that somewhere you're getting stuck in reintroducing body forces, you can let me know. But uh, I think my claim is that it is trivial to reintroduce body forces. If we can just redo the steps because the body forces, the term is quite simple. I mean, of course, not here because I mean this is uh, sorry, this is omega. But in the Navier-Stokes equation, you just have a term which is rho g on the right hand side. Okay. So in the Navier-Stokes equation, uh, this is the equation. Now we will use a vector identity, which is basically this, and rewrite this equation as this. And then we take curl of this Navier-Stokes equation. Now, what this curl will do is it will act on the first term, it will act on u to give you w, omega. And rho basically divide this entire equation by rho. Okay. So the first term gives me del T of omega. The second term will have a curl acting on a gradient, which is 0. So this term dies off. This term will give me this. This is a curl of u cross omega. Then the curl will act on this term. And then finally on this term, giving me this. Now, if you remember, this was 0 for barotropic fluids. And we're still working with barotropic fluids, so this will be 0. We're left with the first term, the second term, which is curl of u cross omega, and then the third term, which is the viscous term. And that is exactly what we had to prove. Okay, very simple, very simple. Nothing complicated over here. Nothing to look out for. Okay, one of the other things that we had also discussed in the live session last week was that circulation is not conserved for inviscid flows. Now, of course, intuitively we understand that because once you have viscosity, you have a dissipation term. You do not expect circulation to be conserved. Now, how do you mathematically show it? It's not difficult. We recall what circulation was. It was the closed path integral of the velocity vector u. Hmm? And then to show that whether to check whether circulation is conserved or not, we had to take the total time derivative of k. And if you look at this term, so of course this term will go to 0 because it's a total derivative. But this term, if from the Navier-Stokes equation, so this combined with this will give you du dt. From this equation, you have this term, which was once again a total derivative. So computed over a closed path integral would have given you 0. But now you have this additional term. And there's no reason why this term should have to go to 0. Okay. So circulation is not conserved. Just a mathematical way of looking at things, something that we had already predicted, and it's quite clear to see. Okay. Now, just like we rewrite the Navier-Stokes equation and computed things in a dimensionless manner, we converted everything to a dimensionless quantity and rewrite it to get this equation. We want to do the same thing for vorticity equation. So to do that, we once again redefine x and u. But now we redefine to get a dimensionless omega, we redefine omega as this. The reason is omega, as you can see, is curl of u, right? Now, omega prime constructed out of dimensionless quantity gradient and u. So if we take this gradient, which is the primed gradient, which is dimensionless, and curl it with u, which is once again a dimensionless velocity, we are bound to get a dimensionless vorticity. Okay. Now we will see what this is in terms of your original x and u and w. Okay. Now if you remember once again, this primed gradient, which is del x prime, is basically, understand that the x prime is x by L. So L goes upwards and you have del x, which is L, your usual gradient. Okay. And u prime is u by u. So you have a L from here. Sorry, this should probably be vector. So you have L from here, which is here, and a u downstairs, and your usual curl of u, which is your original w. Okay, these things should have some vector sign on top of them. Okay, so that is precisely why we have redefined it like this. Do you understand why? Because we want a dimensionless vorticity, which we can get from the reparameterized x and u. Is that fine?
Yes.
Okay, good. And just a second. Yeah. Uh, Remember, we were considering this Navier-Stokes equation uh, for steady flows. So there was a term del U del T which was dropped. So we never had to rescale T, not rescale, redefine T. But T has some dimensions, right? Under scaling, it'll change. So what do? We have to figure out how to redefine T. And it's quite easy. T is basically x by u. We look at how x is related to x prime, u is related to u prime. It gives us this quantity, and you will see that t prime, which is u by l times t, is now dimensionless. Okay, so we have the task of considering the original vorticity equation and making these changes in this equation. And if you repeat everything, just like we did for the Navier-Stokes equation for steady flows, you will end up with this equation. Now, shall I go through the steps, or the slides will of course be uploaded? If you have any questions in between, if you have tried it out and this has not worked out, you can ask me what went wrong, or I'll continue.
I think you can continue.
Okay. So this was the vorticity equation in terms of dimensionless quantities. Okay. Now, the good thing about this is now scale sensitivity is gone. So if you have the same system, just scaled up versions or scaled down versions, the flow profile for these systems will be given by this equation. It will be the same, right? So now you don't actually have to build a ship and put it in seawater and then study it. You can engineer it by building a toy model, but make sure that the Reynolds number for the two systems remains the same. So you have to tweak nu because Reynolds number comes with a combination of u, l by nu. So you have to tweak nu because of course U and L for a ship in seawater and a toy model in a bathtub, they're not going to be the same. Okay, so that's the thing. As long as RE is the same, and that's the principle of dynamic similarity. You have the flow profile around two geometrically similar objects, which are just scale versions of each other, having the same shape. And of course with the same, but this is very important, with the same boundary condition and Reynolds number. The flow profile will be identical if you have the same boundary condition and same Reynolds number. What do I mean by boundary conditions? By boundary conditions, I just mean if this is the object and this is your fluid, boundary conditions would mean the flow conditions right at the surface of the solid object. Okay, so you can't allow infinite tangential slip in one system and have viscosity in the other. You need to have similar boundary conditions because of course this is a second order differential equation. It's just sensitive to boundary conditions. You need to plug in the same boundary conditions in the two systems to get the same solution. Okay. Okay. If that's fine. Okay. So just a very quick revision. Then we considered the special case of Low-Reynolds number where RE is much less than 1, and if it is much less than 1, this term is quite large. If it is large enough that we can ignore this, then all we're left with is a del omega del t del omega del t equals to this term. And for steady flows, this also goes away. Okay, we're left with Laplacian of omega equals 0. Okay, once again, it's a second order differential equation. You will have two boundary conditions. Viscous flows has this boundary condition on the velocity. You translate this to get this, and this was not done in the so this was not derived, but this equation, the solution of this equation gives you Stokes law, which is your usual 6 pi mu L u. Now, what I wanted to know was, it is the solution of this, it has been solved out in some books. I wanted to know whether it would be good for me to actually derive this in a live session, or can I skip it?
I think it will be good to derive this because I don't have the book to refer to.
Okay, okay. I can actually tell you the reference, but it's in Landau Lifshitz. I think it's second chapter, section 16 or something, because the book is labeled by sections. I think it's section 16, if I'm not too wrong. But anyway, okay. Let me look into its solutions, and I'll solve this in the next live session. I'll
Okay, and
actually
one
show
more
you.
thing, like, is it true that if we allow for infinite slip, then the equation will be like 4 pi and instead of 6 pi?
If I allow for infinite slip,
Then will the 6 pi change to 4 pi? Because I heard it somewhere.
I'll have to check. I can't say anything straight away. Will the 4 pi change to 6? Let me make a note. No, so let me see what we are actually doing. We are dealing with Reynolds numbers, which are much, much less than 1. So we're dealing with very high viscous flows. So if you allow for infinite tangential slip, which means you're dealing with inviscid flows, so you're
Yes.
going to what? You're going to if you're dealing with very small viscosities, very small mu's, then you're dealing with very large Reynolds numbers, right?
Hmm.
Uh, but if you're dealing with very large Reynolds numbers, what happens is, as I'll come to it, uh,
Okay, then the Stokes law is not valid at all.
yeah,
Okay, okay, okay.
hmm. Because what one usually see, this is a solution that we could solve for. We could solve for it, and we saw that F has very nice dependence on U, a linear dependence. Sometimes it's not even possible to solve for the exact form. So then what people do is they just, which is what I'll come to next. They just work with some equation, and I'll tell you, I'll come to it. And all of the unknown parameters are taken into uh, account by introducing some some coefficient CD, which is the drag coefficient. Okay, so you work with that relation, knowing fully well that it might not even be the correct dependence, but I mean you keep working with it, and the unknown parameters of the system, like you don't know how the drag force relates to the exactly how it relates to the viscosity or the shape of the object or the orientation of the object. All of those complex parameters are taken into account by the drag coefficient, and the drag coefficient is usually found out experimentally. You see how it varies. You measure the drag force by taking various Reynolds numbers, by tweaking the parameters of the system such that you're considering various Reynolds numbers, right? And then you measure the drag force, and then you plot the drag coefficient uh, with
Reynolds
respect to
number.
the Reynolds number. Yeah,
Mhm.
and you will see that for very high uh, Reynolds numbers, um, you have also, I mean, you have various different features of CD, the drag coefficient. Okay, okay. So exactly as I was saying, if you have a system and fluid flowing through, let's say, a pipe or something, and you have a solid object, and I will not consider a sphere because sphere is, let's say, symmetrical, and it does not matter whether the fluid is flowing is in this direction or in this direction. The cross section that the fluid faces for a sphere is the same because it's symmetric from all directions. Let me consider, let's say, a cube, some weird shape, something, anything. If the fluid is flowing in this direction, and if I say, well, the what is the drag that this object will, so if I want to find the fluid profile, I will have to find the fluid profile around this solid object as well. For that, I need to know, or let's say this solid object is moving with this in this direction with some velocity v. Now I want to know what is the drag force that this object will feel. Now I know one very special case, that if this object were a sphere, and if I was dealing with low Reynolds flows with low Reynolds number, then the drag force is Stokes law. But for any other shape and for any other orientation, by orientation I mean this cube could have been oriented in a different way, let's say at some other angle to the direction of fluid flow. It would have faced a different drag, right? Or let's say the size of this, some other shape. What are the flow conditions? What is the length scale over which the fluid flows? What is the velocity, the characteristic velocity with which the fluid flows? What is the viscosity? And things like this, the flow conditions. So all of these things determine drag forces, hmm, and it's very difficult to uh, compute this drag force from first principles in all of the cases, right? So what one does is one works with this equation, okay? What this CD will do, this is the drag coefficient. What the CD will do is it will encapsulate all of these complex parameters. And of course, you can keep working with it. So, okay, let me not jump ahead. This will vary with shape, flow conditions, etc., etc. This is usually found through experiments, as I said, as was also a graph is also shown in the lectures that what one usually does is one plots CD versus RE. So you take the system, right? You vary the fluid velocity profile, you vary the length scales over which the fluid flows, you vary the different conditions, then you measure this drag force, right? And using this relation, you can get CD. So you plot CD for that particular condition, that is for the particular Reynolds number, and you get some curve, some curve. Okay, that's how it's usually determined experimentally. And once you do plot it against the Reynolds number, the dependence will tell you or will reflect the dependence on viscosity. Okay. Now, okay. Now let's consider a situation for very high Reynolds number. Okay. Which means that the coefficient of viscosity is essentially very small. And so effectively in the bulk, which means away from the surface of the solid object, away from the solid object, the flow is effectively inviscid. But one thing to note is that mu might as well be small. Does not mean this quantity is small. The small quantity multiplied to a very large velocity gradient, and you will have a very large velocity gradient in certain situations that can give rise to a large viscous stress. So high Reynolds number does not tell you, because Reynolds number has no dependence on velocity gradients. Okay, it just tells you that, well, if you have a high Reynolds number, then in the bulk the flow is effectively inviscid. But high Reynolds number does not tell you that the viscous stress on the solid object is low. Okay, so it is indeed important at the object surface, at the boundary, because in a very small layer Y, the flow profile abruptly goes to zero. It sticks to the surface. Okay, all right. But because you have inviscid characteristics in the bulk, that should tell you that the drag, whatever drag the full fluid will exert on this object, that is independent of the viscosity. Okay. So if you want to keep using, because I don't know what the exact relation is, if I want to keep using this relation, then my CD coming from contribution of macroscopic drag, that is from the bulk flow, CD should be independent of viscosity. However, CD will have contributions from viscosity if I'm considering boundary contributions, thus object surface contributions. And of course, it will have dependence on other factors as well. So my point is, I'm using this relation for drag force, okay, where it has a U square dependence, L square dependence. And I'm using this because, why? Because CD now is dimensionless. If I have to construct the relevant dimension full parameters of my system are rho, U, and L. And I have to construct a term which looks like which has dimensions of force, which looks like force, from these three quantities. One way to do it is this. And that and so I can tell that FD is well proportional to this thing. So I'll call the constant of proportionality CD. Now CD can have dependence, may have dependence or may not have dependence on viscosity and other different factors. Okay. But the point is, for high Reynolds flows, the bulk contribution of CD will be independent of viscosity. That is what the lecturer also claimed. Is this part clear? Because this part could be confusing.
Uh, the last part, can you just repeat once?
Okay, which one? Which one? Tell me.
The what you said last.
Okay, okay. You agree that for flows with high Reynolds number, the coefficient of viscosity is indeed low,
Okay.
right? If mu is small, that means I can consider the bulk flow to be effectively inviscid.
Okay.
I can drop terms which have viscous stress, which represent viscous stress because mu is small. But
Okay.
remember that viscous stress also depends on this gradient, which is also small throughout bulk. So both of these quantities are small, hence that allows me to consider inviscid bulk flow. But as I come near the surface of the solid object, which is immersed in the fluid, what happens is this term starts to grow, and it grows in a very short length scale. So this term is actually very large near the surface, hmm, which
Okay.
tells me that viscous stresses are actually very important near the surface of the object, right? So the drag that the bulk of the fluid will impart on the solid object will not have contributions from viscosity. Do you agree with that? Because viscosity is negligible in the bulk because of
Okay.
high Reynolds number, right?
Hmm.
But contributions from the boundary, or rather the boundary drag contribution, will depend on viscosity. It will depend on a lot of other factors. It will depend on the shape, the orientation of the object, and so on and so forth. Do you agree?
Yes.
That is all I wanted to say. I am using this relation. I'm
Okay.
using this relation.
But why did you put an extra half? Because this can be absorbed in the CD.
Sure. I mean, this is just convention.
Okay.
Sure. Okay. It's just convention,
Okay.
right? So this CD, this CD for the macroscopic, or rather the bulk flow drag contribution, is independent of viscosity, whereas for the boundary drag contribution, it does depend on viscosity.
Okay.
This point could have been confusing from the lectures. That is why I wanted to emphasize this.
Okay.
Okay, good. Okay, now comes the plot that was shown in the lectures. And if you remember, the solid line were actually data points from experiments. Hmm. And this dashed line marked as Stokes is what one would expect or predict from Stokes' law. Okay, and to see why it's a straight line, so if it is indeed a straight line, we should be able to see that from Stokes' law. Okay, so what we will do is we will equate Stokes' law. This is Stokes' law to the usual drag force law we usually consider, which has a drag coefficient in it. This will tell me that CD is actually 1 by Reynolds number. Okay, is this clear?
Yes.
Now my question is, if CD is 1 by Reynolds number, why is this plot straight? This because a straight line, this is not the equation of a straight line. Any guesses? Any guesses? The hint is look at the axis. Look at how the axes are marked.
Oh, because it's a logarithmic scale.
Absolutely. It's a log-log scale. And I wanted to point it out because as you go along the course, you will see in multiple scenarios that the axes are usually marked logarithmic in log-log scales. So you will see a lot of straight lines here and there, and the relations will be like power laws and stuff. So don't get confused there. Okay? Because you'll mostly be dealing with log-log scales in astrophysical systems. All right. We are almost at the end of our live session. Let's discuss a few sample problems.
Okay, just one question.
Yeah.
Why does this vortex shedding take place?
Why does it take place is a very I honestly I don't have an answer I can give you. It is something that's very complicated, not very well understood even. Uh, so to be very short, it's something just be aware of when it happens, in what Reynolds number range it happens, and of course it'll be fantastic if you're interested in it and you want to read up on this further. But right now, I do not. Uh, at this level, there is no good way of explaining why this vortex shedding.
And
It's a
actually,
very complicated
I mean,
process.
is it the same phenomena which actually happens in the submarine blades and all?
What happens in submarine blades? I'm sorry.
No, actually, a long back, actually, I read about some phenomena in which the formation due to high velocities, there is a formation of bubbles, which actually small liquid-free zones, which can actually
Okay.
damage the submarine blades and all.
Okay. Okay.
Is it a similar kind of phenomenon, or is it something different?
Vortices are not fluid-free zones. They are regions of extremely high curl U regions.
Okay,
Uh, but mm, but I'm not sure whether I'll have to read up on this then. The damage of submarines done by fluid-free regions. Okay, then I'll have to look into it. I don't know if it's the same thing. But see, I don't think submarines have such high velocities to reach such large Reynolds number. I don't want to make this statement because I genuinely don't know, but it feels like, naively speaking, to me, it feels like submarines would not have such high velocities because these things happen at really really large uh, Reynolds numbers. These happen at very large flow velocities. Okay,
okay.
so I'll have to check up on it. Let me read up on it and then I can clear it in the next live session.
Okay, and one more thing that like Professor Prasad, as he mentioned, like in as we can see this dip in this graph,
Yeah, yeah, yeah,
he
yeah,
talked about this supersonic flights, and
yeah,
he said one must be careful about this region because actually, means does it mean that it can cause instability and stuff like that?
yeah, yeah. Because you want your aircraft to accelerate or reach or operate at a certain velocity. Now
Yes,
you're applying a certain amount of thrust to it. Now
yes,
you suddenly see that beyond some velocity, you have a sudden acceleration, a sudden jerk, and that can damage aircraft parts. And you have a
okay,
sudden jerk because your drag drops. So
okay,
the drag that you had to overcome to operate the aircraft at a certain U required a certain level of thrust. Now, as you're slowly increasing thrust and going to higher U's, you suddenly see that after a certain value of U, there's a sudden dip in drag coefficient that will jerk the aircraft and that can damage aircraft parts. So one has to be careful where this dip comes in. It's an engineering application.
okay. But
Yeah.
means how does the pilot come to know about that? I know it's
Uh,
I'm going off topic, but just
yeah, yeah, but I think so. See, I'm no expert in this as well. My guess would be that you already know, you have already operated. So whenever you're operating a very, an aircraft which is equipped to or built to take such high velocities, you know under which velocity range, what do you have to do to the aircraft? When do you have to control your thrust? When do you have to be careful about, I don't know, the windshield flying off, things like this. So these things are, I think, modeled. These things are known.
okay, okay.
Yeah, yeah. That's nice. That's nice. So since I don't work in these things, I will not be able to provide you with answers like this. But yeah, these are nice questions to ask. Absolutely, really nice. Okay, so consider a smooth, solid metallic sphere moving through a fluid. The Reynolds number is 10 power 4. Will the fluid not stick to the surface of the body?
No, it will stick.
It it will stick. Of course, it will stick. I mean, because the Reynolds number is not infinite,
Yes.
because the fluid would have not stuck to the surface if the Reynolds number were infinite, if the mu were exactly zero. Mu is small, that's why the Reynolds number is high, but the fluid will of course will stick. Okay. The drag experienced by the sphere will be proportional to the square of the relative velocity between sphere and fluid.
True.
Absolutely, because of the force law that we are using. It goes as u square. Fd goes as u square. The total energy of the fluid will be exactly conserved along the streamline.
No, because it will be dissipated in the form of vortices.
Absolutely. Mu is non-zero, first of all. Absolutely. The drag experienced by the sphere will be proportional to the relative velocity between sphere and fluid.
No.
Because of course B is correct.
Hmm.
So the correct answer is B. Okay. Now consider a pipe of cross section 2a. So this distance is 2a. And it's filled with viscous fluid. And the fluid is flowing along the x-axis. And it's flowing as response. Okay, so this is because of the way I've attached this picture. This should actually be dpdx. Okay, so the fluid is flowing as a response to the pressure gradient along x direction, which is a constant pressure gradient k. Okay, now we have picked the correct options where the fluid will accelerate along the x direction and so on. So will the fluid accelerate along the x direction?
Uh, yes.
Why will it accelerate along the x direction?
No. If it is a steady flow, then it won't accelerate.
Absolutely, absolutely. It's a steady flow. It's in the question. Correct. Now the shape of ux as a function of r will be Gaussian or
It will be a paraboloid, not a Gaussian.
absolutely correct. Correct. Now whether it will be r square or r4, that's something we have to find out. Now this was done in the class, so I'll because he discussed the solutions of the equation. So I'll just very quickly go through it, but the boundary conditions were not exactly discussed. So I found it worthwhile to go through this once. So given the flow is this and the pressure gradient is this, now the Navier-Stokes equation is basically this, okay? Neglecting body forces. Now once again, since we are dealing with steady flows, we will ignore this term, right? And what else? Yeah, and we know that the gradient of P is K, right? And if U has such a profile, you will see that this is actually zero. So I had actually solved this boundary condition problem in Cartesian coordinates. This is the same exact problem in cylindrical coordinates. Exact same problem. The same velocity, the same pressure gradient has been applied. You will see that this term actually goes off. So all you're left with is this and this term. And if you match the components, you will end up with this solution. This was done in class, okay? In case you don't recall, this was third week where he discusses the boundary conditions of Navier-Stokes equation and getting a solution. Okay. Now, A and B are constants introduced while solving this second order differential equation. Then we have to set them by setting the boundary condition. Now, clearly, one of the boundary conditions is since we are dealing with a viscous fluid, at the surface it will stick. So U at R equals A will be 0, right? And that gives us this equation. You just substitute R everywhere with A and set it to 0. The next condition that we can use is that at R equals 0, U is maximum. Now, can you tell me why?
What did you just say?
The first boundary condition, we need two boundary conditions because we have two constants to set, right?
Okay. Hmm.
One of the boundary conditions is that it will stick at the surface,
Yes.
right? So that is what we have said, and we have obtained a relation between A and B. But we could not remove any of those. We need another boundary condition. Now, my claim is another boundary condition is that U at R equals 0, which is basically this line, is maximum.
Yes.
That's what we do. That is what we do. We say that the fluid has maximum velocity here, and as we approach the surface, it goes off to 0,
Yes.
right? So if you do this at R equals 0, you need this to have 0, you need this to be 0, but you have 1 by R here. So you need
Okay.
A to be 0,
Mm.
correct? So you need this contribution to just not be there. Otherwise, this will cause divergence problems. This will blow up.
Okay.
But you need du dr to be 0. Okay. So you set A to 0. You set A to 0 in this equation, and you get B as minus Ka square by 4 mu, as so. Okay.
Okay.
So this was your UR, and you substitute the value of A and B, and you get this. Now you will see that this option comes with a minus sign over here. That is because you had taken dp dx to be plus K, which means that the fluid should flow in this direction. So this option should be correct. But what the question actually means is there is actually some problem. This should be minus K if the fluid flows along this direction. This is something we had also discussed while solving for the solutions of Navier-Stokes in Cartesian coordinates with boundary conditions, that you should actually have a minus K over here if the pressure gradient, if the fluid is to flow from this point to this point, then the pressure over here has to be greater than the pressure over here. So P has to actually fall along X. So this should come with a minus sign. Okay, if this comes with a minus sign, K itself is negative and you get the correct sign over here. Okay,
Okay.
okay, cool. Okay, the coefficient of viscosity is related to the momentum flux. Is this correct?
Mm, true.
Very good, very good. Remember that momentum flux, you have to think back to transport phenomena, that if you have a non-zero momentum flux, then you should have viscosity. This was, remember when we force balanced and we said that, well, there should be viscosity because you have momentum flux. So option E is correct. The coefficient of viscosity is related to heat flux.
If A is correct, B should be incorrect.
Mm, That's, well, heat flux does not relate to viscosity. That this comes from the relation between the microscopic and macroscopic description. Heat
Mm.
flux actually comes from something called the thermal conductivity. The coefficient of thermal conductivity is related to the heat flux. So D is correct and A is correct. Okay.
Yes.
Now, option C is the shear stress tensor is traceless.
No, only the diagonal components are the shear stresses.
Uh,
Oh, no, 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 no. I think I'm
yeah.
so
So
it's
let me
correct.
let me remind you that Pij, I wrote this as some one third P uh, delta Ij plus sigma Ij, where this part was the diagonal part, right? So if this is a 3 cross 3 matrix, let's say, this would be the 3 cross 3 identity matrix multiplied to P and some matrix. Now, understand that since P arises in the diagonal parts, P is what is written in the diagonal elements. So P encapsulates all of the trace. So this part has to be traceless if the trace of both of these sides have to match.
Yes.
Okay.
Uh,
So the shear stress tensor is indeed traceless. So sigma ij is the shear stress tensor.
mhm,
Ph is the full pressure
mhm.
tensor, which has the pressure part, the diagonal pressure part, as well as the shear stress tensor part. Okay.
I said just the opposite.
Yeah, yeah. That's fine. That's fine. Okay. Last question. Consider a horizontal stream of very high Reynolds number fluid hitting a vertical wall. The coefficient of viscosity is high close to the wall.
Coefficient of viscosity is a characteristic of the liquid.
Absolutely, absolutely. Coefficient of viscosity is something that does not depend on the flow conditions. Coefficient of viscosity, coefficient of dynamic viscosity is something that is given to you, allotted for every fluid. Okay, so it does not depend whether you're looking at the fluid very close to the wall or in the pipe. It does not matter. Okay. So of course this is wrong. Now the coefficient of viscosity is quite small everywhere, but this term in the Navier-Stokes equation is significant near the wall.
True.
Very good. Let me go through the logic of why it's true. So I can tell that the coefficient of viscosity is quite small everywhere. I can claim this because the Reynolds number is very high. Because the Reynolds number, remember, was sum u into sum L divided by nu. Okay. Now this, if this is very small, that is when I expect Re to be this large. Okay. So I can claim that coefficient of viscosity is quite small everywhere. But this term in the Navier-Stokes equation, I can ignore this if this Laplacian of u is small, if the velocity gradients are small. But when the fluid hits the wall, it abruptly comes to a stop, and that's when the velocity gradients are quite large. And when the velocity gradients are quite large, then this term becomes significant. Even though mu is small, it's a small number multiplied to a large number. And this can have significant contributions. So one needs to consider this contribution when considering the region when the region near the wall. Okay, so this is true. Okay, the term L omega by u is dimensionless, where L omega u are your length, vorticity, and velocity.
Correct, because it's just discussed.
Correct, absolutely. Just to recall, this was curl of the vorticity was curl of u, right? Now, if I have to consider a dimensionless vorticity, I have to consider a dimensionless gradient curled by a dimensionless velocity. And if we looked at how to get a dimensionless gradient and dimensionless velocity from these dimensional quantities, it will give me a factor of L by U. So C is correct. D. The coefficient of viscosity is quite small everywhere. Consequently, this term, so clearly, as we discussed, B is correct. So D cannot be correct. We do have to consider the contribution of this term near the wall. Okay. All right. So I'm done with everything I wanted to discuss. If you guys have any question, you can ask. So Aniket, as far as I remember, you were interested in uh, one thing was why exactly you have this vortex shedding. I can look into why if there's a simple way of looking at it, uh, because I am myself not an expert in this, so I stay really far away from such complicated things. But I'll definitely look into it if there's an easy way to see why it's happening. And another question was this. Uh, Analogy between the submarine fluid free regions plus this vortex shedding, whether there's a relation, whether they're the same phenomena, right?
Yes, yes.
Okay, I'll look into this and we can discuss this the next time.
Okay.
So, are there any more questions? If not, then I'll stop recording and I'll wait for a few more minutes in case any of you have any questions.